surface area of Gabriel's horn, which is the figure formed by rotating 1 over x from 1 to infinity. So what method are they using for volume? Disk. Thank you. That's what I was looking for. Disk method, because pi r squared. And it's easy, right? Because it's there's no hollows. There's no reason to go into shell. There's no reason to go into washers. So yeah, just disk method. Why couldn't we technically have solved this before now? It's an input integral, right? Oh my. So go ahead. Ready, set, go. I'm going to give you guys like a 30-second head start, and then I'm going to bust it out. Which one is finite and which one is infinite? Well, it does say in the wording, but let's see if the math matches that. And then I'm going to do a really nifty little trick on the surface area to avoid us having to do trig sub, which we could have done, but I'll do a nifty trick. Yeah, you do. Pythagorean theorem. Make a triangle. Well, if we rewrite first, we can. He's going to use the p-series thing. I'm going to solve it the old-fashioned way. Oops. Definitely should have written my limit first. For those of you just joining us, we basically talked about life for most of class, and right now we're doing a little bit of work, and then I'm just going to let them loose because this weekend's homework is really just to finish 9.4. If you haven't finished it yet, get it submitted by Monday. We'll grade on Monday, but also start the review. So Monday is our work day on 9.4 questions and review questions for the test on Tuesday, which is a chapel day because of spiritual emphasis week. Did I get the highlights? Yep. You guys agree? Oh no, my limit. Ugh, I'm a horrible person. Oh no. There we go. Now 1 times pi is pi, because 1 was from here, and then got it. Are we good? Improper integrals? Okay, but what's going on with the surface area? Do you guys remember that formula? 2 pi r times the arc length, right? Arc length means the square root of 1 plus f prime of x squared. Arc length of anything but parametric curves, which we saw that there might be another variation to on the Barron's exam, but that's okay. So this one, who's your r?
Radius.
Yeah, and what represents your radius? Depending on your orientation, you could do top minus bottom, and it could just be y, but what's everything in terms of this time? So what we're going to do instead? X. The surface area isn't one that you really have to visualize. Remember? It was one that you can make it in terms of x or in terms of y. Like arc length, how you can do in terms of x or in terms of y, whichever one is more convenient. We can do that with surface area too. So without going any further than that, we can just go ahead and plug in from 1 to infinity of our x square root of 1 plus. What's the derivative of 1 over x?
1 over x?
Derivative, you integrated.
Oh.
Is it? Why? Hold on, pause. What's the derivative? Good. Negative 1 over x squared. Squared would be 1 over x to the 4th, right? I know it says it's infinite, but let's show it mathematically. That's basically what we're doing. So what is the volume? Pi. Really? Like as you keep on going, it approaches 3.1415926? Maybe that's how they discovered pi. It's not. They measured across and they measured around and they divided. But that's okay. Keep going. The Bible has pi. 22 over 7, so a fractional approximation. And it said the earth was round, the ring of the earth. Interesting. Before all the philosophers got there. Well, they killed the one. Poor guy. Coming back. How do we simplify the integral to try to solve it? Common denominators look good? So then be x to the fourth plus 1. Oops, that's a 4. And then it's over square root of x to the fourth, which is x squared, right? So we could pull that out because we know that integral. We could do 1 to b if we wanted. We could do 2 pi, and then we could do the limit as b goes to infinity. So I made it x to the fourth plus 1 over x to the fourth. I square root of the x to the fourth, which is x squared. Don't need absolute value bars because x squared is always positive. No big dealio. And then I can simplify that, right? You suppose? Which ends up being of x to the fourth plus 1 dx. Wait a minute. Hold on. Why is this not looking right? Doesn't look the way I wanted it to look. Oh yeah, it does. It's all right. Could we try to play with trig sub and try to play with integration by parts maybe? Or try to play with, I guess we could make this 1 over the square root of x squared, and we could bring that in, and then we could try to play with that with integration by parts. Trig sub, yes. But is it a messy integral? Do something like this. Instead of equals, let's do greater than. And you're like, wait a minute, what? And what if I was to do limit as b goes to infinity of 2 pi times the integral from 1 to b of 1 over x times the square root of x to the fourth? Am I right or am I wrong? Whatever this is it going to be bigger than this? Yeah, why? Yeah, that one has a plus 1. Which adds the magnitude. How much? I don't know. But it's a little bit bigger at least. True? So mathematically speaking, could I solve this integral and say that that's going to be a little bit bigger? Now, if this is a constant idea, I don't know, something bigger than that constant. If this is infinity, though, what's bigger than infinity? Oh. This one nice. What's the square root of x to the fourth? X squared. What's x squared over x? X. So when I go to integrate x, I can go ahead and say, oh, it's going to be 2 pi times 1/2 b squared minus 1/2 times 1. What happens as b goes to infinity? P.S. I integrated 1/2 x squared, or x squared over 2, and then I plugged in b and I plugged in 1. That's growing without bound, true? So what's the whole thing? And if mine is greater than, then what does that mean about my surface area? It's infinite. But you might be like, okay, that was a nifty trick. We're actually going to use this nifty trick a few times in chapter 10. But for right now, we kind of used it back in the day with optimization problems with distance, closest and farthest, but maybe you don't remember that. But anyway, long story short, interesting. Gabriel's horn, a finite volume. We'll keep approaching 3.1415926, but an infinite surface area.
So I have a question. So just from looking at the graph, you can tell that like the arc length is infinite because it keeps approaching. So from the graph, what you just said, it's like infinity.
In some ways, shapes, or forms. Mathematically, I think you'd have to. You couldn't separate the x from the arc length to actually show that. Does that make sense? So even though in your head it makes sense, mathematically we'd actually have to work through the integral in some way, shape, or form, because we can't just like plug in an infinity for the arc length, because that would be the integral of the square root, which there's no product property to separate. Does that make sense? But yeah, that makes sense. Do you guys hear what Aryan said about the infinite arc length is going to keep on adding, as opposed to the volume that's going to converge? Interesting. So the test review, not due on Monday, but if I were you, I would try to attempt it as much as possible. I'm going to go ahead with the last 9-10 minutes of class. I'm going to try to do my nifty little, like, take pictures and then throw it up with the answers, right? Is that what I do? It's been like a month or two on the test review in Google Classroom. And then I'll let you guys, if you want to borrow a book, you can borrow a book. If you want to take pictures of someone else's, you can take pictures of someone else's. I have 3 up here. If you want to talk more, reminiscing about life, you can do that too. Or you can do all of them at the same time. Ready, set, enjoy the last 10 minutes. I'm still here. I'll still be participating, but I'll be working on that Google Classroom thing for you. Okay.